also has some things that make it not overwhelming. So, as you guys probably already know and have heard me say before, when we do stoichiometry, we kind of assume something. You guys remember or have any idea what we assume when we do stoichiometry?
Is that equilibrium?
Okay.
That is an isolated reaction. Nothing else.
Okay. And I realize that's probably a really broad question.
You assume that nothing's escaping and we need to react.
Those are all
That's
pretty good
spontaneous.
assumptions.
That's
Yes.
spontaneous. Is that what you're going for?
Completely, right?
Yes.
Oh, yeah.
We assume that when we do stoichiometry, that the reaction goes until all of either one reactant or both reactants have been used up completely. Well, believe it or not, this is not the case all of the time. It is the case some of the time. Okay? Now, do you remember what has to happen for equilibrium to occur?
The rates of the first reaction and the reaction to be the same.
The rates of the what? The what?
The forward reaction and the reverse reaction.
Yes.
to equal.
Okay, if you do not have that down, you should write that in your notes somewhere. Okay? Equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. Now, I feel like you've heard me say that a lot. You may not have a problem with that, but just in case, it wouldn't hurt. The rate of the forward reaction equals the rate of the reverse reaction. So, there is some situations where it does go to completion. Like if I were to put hydrogen gas and oxygen gas in a chamber together at specific temperature, it would essentially react to the point where you would be able to pretty much say that there's a negligible amount of reactants left over. However, there's other reactions, usually the decomposition reactions, okay, because they need heat to usually decompose. Those reactions, we would say, don't react hardly at all. And so your equilibrium point of that is not completion. So, what you end up with for chemical equilibrium, this is another way of stating what chemical equilibrium is, and I'll explain why I kind of like the definition of chemical equilibrium I gave you a little bit better, because a lot of times kids get confused with the fact that it's talking about concentrations. It says the state where the concentrations of reactants and products remain constant. This is the key word here. What does that mean?
They don't change.
Okay? So equilibrium is when your reactant concentration doesn't change anymore. Sure. The net change.
Yeah. Oh, yeah.
Okay? So, where the net change of your reactant concentration, the net change of your product concentration is constant. It doesn't appear to be changing. Okay? Now, the reason why I tend to give you this definition that I had you put in your notes and not focus so much on this is because a lot of times people think, oh, does that mean that the concentrations of reactants and products are equal to each other? No. Now, could it? Is there one possibility where you could have 50% reactants and 50% products? Now, but that's only one point of all the possibilities that you could reach equilibrium for, right? Okay, you could have 51 and 49, 52 and 48, and then you could throw in all the decimal numbers in there too, right? Okay, so could you reach equilibrium where you have 50-50? It's possible, but it's fairly unlikely. Okay, so the idea here is that chemical equilibrium means that my concentrations don't change anymore. That could be a variety of places. Could be all the way to completion. Could be far left. Could be you name it. Okay? So I think you're at least familiar with these two concepts or have heard them before. Skinheads?
Part of the right and part of the left is that toast. That was making a joke.
Oh.
far to the right, far to the left, up. Okay, never mind.
And that audience is key here. I don't
That's
read.
That's true.
Well, that's not true. I'm currently reading 2 books, but
That's on the camera. Hello, camera. Kramer does in fact read. He's the smarty pants.
like 3.
He likes books.
That was a one-time deal. Okay, so what do you guys remember about far left and far right? What is that referring to? If I say a reaction's far left or far right,
It's not 50% like you said, but it's shifted one way or the other.
now we will talk about a shift in equilibrium later, where we actually are at equilibrium and then we do something to cause it to shift one way or the other. But when I say far right or far left, that means when I'm at equilibrium, yeah, do I have mostly products or do I have mostly reactants? Because at equilibrium, our concentrations are what? Yeah, constant. Okay? So if I'm at equilibrium and I have 80% products and 20% reactants, how would you define that? All right. Okay, or product favor would be another way of saying that. Okay? And I could say 10% product and 90% reactants would be what? Okay. Now today, I'd like to have had the test graded so that usually I have a smaller lesson the day after a test because we have to go over the test and that takes time, but that's it. Now, you should remember this idea, this concept from last year as well, dynamic. What does dynamic mean? Yeah, okay. So equilibrium, when we talk about equilibrium, a lot of times we get in our head that the reaction just all of a sudden stops once you get to that point. Okay, it's not the case. There's a few analogies I can give you. It would be like there was a bridge connecting 2 cities. Cars are going back and forth between the 2 cities, and let's say you had the same amount of cars going back and forth. Okay, does that mean there's no activity?
No.
No, there's activity, but the net overall change is constant. Okay, another example would be you had a hole in your boat and water was pouring in. If you were flipping the water out at an equal rate the water was coming in, you wouldn't see any change. You're at equilibrium, but it's dynamic. Okay? So, all I want to end with here then is this. Just to make sure we understand the concept of equilibrium and what it means, because it's so important for what we're about to do. We're going to see our double arrows now. Why is that?
Because it's both directions.
Okay? Technically, every reaction should be a double arrow reaction. Okay? At the start of the reaction, we're going to assume that, now this isn't always the case, but for this purposes, we're going to assume that we have all reactants. So let's kind of talk about over time what is going to happen with relating to concentration and rate. Since we just got done with doing rates and kinetics last chapter.
You said we have all reactants.
Yeah.
Products.
Yep. So let's just say, we'll say time 0, we'll go time, I don't know, 100 seconds, and then we'll go time equilibrium. Okay, time 0 seconds. What could be said about the concentration of your reactants and the rate of your forward reaction?
Slow down as the
Just at time 0.
we get highs there.
100% concentration. Whoops.
And the rate the fastest it ever was.
Yep. How about your products?
The reverse would be 0 for rate.
And
0%.
so reverse, forward. Okay, now we're not at equilibrium, so what would you expect us, we would probably, which way are we gonna shift? We're gonna shift towards the product or towards the reactants when we start this? Yeah, right? Okay? Let's say, I don't know. I'm gonna go ahead and say, we're not that close to equilibrium. We got 70% concentration. Okay, let's figure out what can be said about the rates of the forward and the reverse here. I'm just kind of doing this on the fly.
Yeah. The rate would be still fast, but not as fast.
Okay, why would it be slowing down?
Because it's less concentrated.
Okay, can you explain that in the context of last chapter?
Less collisions.
Less collisions, okay? So, you could say fast.
Ish.
Fast-ish, sure.
Okay.
If you get, it almost looks like fartish.
That's not
Fast.
what it looks like.
Fast-ish. I don't know, there's not a great way of describing this without using a paragraph, probably.
Yeah.
To say, it's slower than what it was at 100%. And the reason why is because you have less concentration, so you have less collisions that can possibly happen, so your rate's going to slow down. My socks.
I do.
What are the colorful socks do?
No, they got a belt from them.
I think mine's a
Those are
reindeer.
weird.
Well,
Annabelle. They're similar. They're basically the same thing. What was the advanced camp where teacher and his sister-in-law compare their socks?
mine's prettier. Okay.
His
Oh
are
my
prettier.
gosh.
I got prettier elk. My elk are prettier than yours. Okay.
All teacher classes.
What'd you say?
Don't be sick on this day.
Don't be sick on this day.
Yeah, because it's
Well, that would be the perfect thing if you wanted to see it, to be sick, so therefore you had to
Yeah.
watch it.
yeah. I'm saying don't be sick on this day next year unless you want them to watch this.
Oh. There's far worse videos
There-
that we
there-
can watch.
there are.
Alright, so what can we say about the reverse reaction?
It's speeding up.
Yeah, so I should say fast-ish, but maybe that's a good way of doing this. Slowing down. So it's still fast, but it's slowing down. We should be at about 30% product. Now, depending upon the coefficients, you know, it's probably not completely accurate to say 70%, 30%. Okay, if you know what I'm saying.
Yeah.
Right? So here we're speeding up. And let's say medium. Again, this is all like big picture here. I don't really have numbers to go with these. This is all okay? So the point here is as this starts to react, the concentration is going to go down, and because the concentration goes down, you have less collisions between your reactants, so therefore your rate of going forward is going to slow down. Well, as your products get produced, your concentration goes up, the possibility of your two products to come and collide into each other is going to increase, therefore the rate of the reverse reaction will start to speed up.
It's like a seesaw. If downward pressure was concentration, you're pushing the other one.
Sure, except for it doesn't go back and forth over equilibrium.
It's true. But eventually equal.
Sure. Okay? So let's say we're at equilibrium, and I'm just going to go ahead and say it's not 50-50 here, because I don't want to confuse you with that. Let's just say we are a product favored, and so let's say we are 35% and 65%. So what could be said then about your rate? reverse of the world. Now, don't get caught up in, okay, well, how fast is that or how slow is that? That's not that important, okay, because this is all just in theory here. I'm not mean numbers with this stuff, it's all theoretical, conceptual at this point, okay? We will get into doing some heavy math with some of this stuff, being able to predict exactly what the equilibrium concentrations will be. We'll be able to predict if I caused a stress to equilibrium, which way it would shift and how far it would shift. We're going to be able to do that as we progress, okay? So this, what we're doing here was just theory. Okay, any questions? I know a lot of this was review, but we have to have a really solid foundation of this because it ends up being more conceptual than you think.
With a reverse rate,
Uh-huh.
equilibrium is the fastest it will be, correct? Will it be?
Depends. You could, in theory, start with